We're going on to where we're going to do a transformation, an exponential model, and that is when one of your axes, the x-axis generally is not transformed. It's going to stay as it was, but the other axis, the y-axis in this case, is going to get transformed either using a common log, which is a base of 10, or a natural log, which is base of y. I mean, you could use other bases, but the two that are most popular are definitely the common log base 10 and the natural log base e. So here is this data, and they're using Moore's law to predict the number of transistors that are going to be in an integrated circuit chip. And so we have some mini tab output right here for this model, and it says that this model involves the natural log model for y. So here's my y list, and they didn't, and let's say that's in my L2 on my calculator, which it actually is. They would have put in L3, they would have put natural log of the L2 list, and that makes it the natural log of y. And so that's going to take these numbers that you see increasing by ginormous magnitudes, and it's going to then turn them into exponents instead of numbers in in our normal system. It's turning them into exponents, which is going to make them much smaller and more manageable. This is the x-axis here, probably an L1. This is my x-axis. But when I look at what they say here in the mini tab output, the x is actually years since 1970. So they actually did do a little transformation on their x. I need to take my x and subtract 1970, and then that is going to be, or actually my x will be, I'll write it like this, my x will be the date minus 1970. So when you have 1970, it's going to be a 0, and so this one should come out as 1, etc. All right, so we want to determine the model that relates the years since 1970 to the number of transistors. So it looks like we have the natural log of y. Don't forget to put your hat above it because this is a prediction. All right, so that's our model. So now I'm going to write what that is. That's equal to, and so here's my y-intercept right here. So my y-intercept 7.0647, and then here's my slope in the output. So, and it looks like it's a positive slope. So if I was trying to find my r, I would need to make sure when I did the square root of r squared, my r would be positive as well, but 0.36858. And then in here, I'm going to put years since 1970. So, or maybe you want to put, instead, you could put date minus 1970 in there. Okay, and so, or actually I could, since I used a y, I could have that just be an x instead and put my, I'm going to do that. Make this an x. Okay, but what is x? X equals date minus 1970, or years since 1970. Y equals the number of transistors. Okay, so there's my model, and I've defined my x and my y since I was using x and my y when I wrote this model. So now let's go over to the calculator and work with this. Let's say that I was going to use this model before I go over to the calculator and show you how I would work with this and create a model with this. Let me show you how I would solve for a certain year or a certain number of transistors. Like, for example, if they said use the model to find Y in 2007, which is appropriate in our model because that's right in this group of dates. All right, so how would we do this? I'd take my natural log of y, I'd say 7.0647 plus 0.03650, and now I'm going to go 2007 minus 1970, and then let's see what that is. Punch that in the calculator. Natural log of y. That comes out to be, and this is right here is 37. So when I punch that in, I get 20.6. So how do I solve this for y? The inverse of a natural log is the base of e. So if I take the base of e on both sides, that will cancel my natural log with the base of e, meaning that my predicted y value, if I slide this up, will be, and then on your calculator, you should have an e, which would be right there on the same key as the natural log. It'd be the second plus natural log. So e, raise it to the 20.6, and that means that I predict that we're going to get 88402863.9, but realistically, this really implies some precision that I don't really have. That's probably, I would just go with 3 sigs here. So, because I'm not really going to be precise all the way down to that. So I predict that we get 884,000,000. So I would say 884 million resistors is what I predict for that year. And then if somebody asked me to then make a prediction for the year 2025, well, in that year, you could plug it in, but I think once you see the result, you would realize that it's well beyond the last year being 2010. This is beyond the dates of the model. Okay, so it's beyond my model data. So what do we call that when we have something like that? It's extrapolation. And so it would not be appropriate to use the model for this date. Now, I mean, somebody might do it. I mean, we're getting close to 2025. Maybe they could use this model for 2021 or 2020 and like see what it gets. But, see how it did pan out with, now we're in 2020 and 2021, but whoops, appropriate to use this model. Okay, so there's that, and if you were interested in what the R value is going to be for this, I can go up to my output and I can look at this output right here. My R value would be the square root, and it would be the positive because the slope is positive. Remember that the R has to agree with the slope. My R would be 0.994. If I look at this model, my residuals is basically off by a very small amount. Of course, that is in logarithm, in natural log. So like that, it's only about half of the units would be natural log of transistors. And if you look over here, what kind of evidence do I have that that a linear model, that there is some kind of a relationship, well, a p-value of this a t of this. So if I was doing inference on that slope, I would say that since the p-value of 0 is substantially lower than 0.05, or even you could change your confidence level to 0.01 or something, it'd be lower, but that there is significant evidence in this situation that there is that linear relationship for this model. Okay, so I'm going to just go to my calculator, and I'm going to just show you how, like, if you had to generate a model, you didn't have the output, and you had to generate a model using this data. I'm going to show you how all the steps that I would have done to do that, and finishing the steps with the checking the conditions, just because that might be the last thing to check. Okay, so here's the transistor data in my calculator, and first thing is they did say that they were transforming their x values by subtracting 1970, so I'm just going to take my L1 list, and I'm actually going to keep myself in L1, and I'm subtracting 1970. If you want to put it in a different list, you of course can, but this will just fix that list so that that's my x value that I'm going to use. And then, because I want to keep this original data here, I'm going to put in here the natural log, and that's just, I usually go with the natural log, which is the base of e, but it really doesn't matter if you want to use the common log, which is base of 10. You want to be able to work with either one of those things. But here's the natural log. So these would be the exponents for these numbers over here if I'm creating that number with a base of e. And I'm just going to put in here, just to show you that the common log, it really doesn't matter. I'm going to put common log, that's the base of 10, common log, and I'm going to do that with the L2 list, and I'm going to put that down here. So those are different numbers there, but watch what happens when I generate my equation using linreg. So stat calc linreg L1, and I'll put L3. So this is going to be the natural log, and I'm going to calculate. So I get, there's the form. So remember, it's natural log of y is going to be 7.064699 plus 0.365835, and then x, where x is years past 1970, and that gives me an r equal to 0.994304. Pretty nice. Actually, I'll write down all the numbers, 1878. Okay, just to show you, then if I do this exact same thing with the base of 10, so that would be the log with a base of 10 of y. We don't have to write the 10 because this is the common log predicted value. If I run this again, I like 8. Do this with the L4 list, and boom. So like actually ends up with slightly different numbers going into this. Okay, that's the y-intercept plus 0.15888, and then x years past 1970, but the r is actually the same. So it ends up being the exact same value. And then, so that generates some equations here. We can also look at the residuals and all that to check, does this seem to make sense? But before I do that, I just want to try one other thing. If I go to stat calc, and if you look down the list here, there's actually a natural log regression and an exponential regression. And if I say do this linreg, because like let's say I didn't know which one it was supposed to be and I just did it with the original data, and I go down here, that gives me a pretty bad R value, because what this one would have been doing is taking the log of the x, you see, so that's not what I wanted. But I can actually get the transformed version of this equation right here, transformed, where I've taken the base v on both sides. Stat, calc, so it wasn't the natural log regression, but if I do exponential regression on my L1 and L2, you can see that that gives me the same R value, but it changes the format of how this equation right here was written. That changes the format of that. So this actually is another way to say the exact same thing. I would get the values, and then my base is 1.4417. That's good enough. And then raise it to the x, where x is the years past 1970. That actually works as well. And how would something like that be discovered from this right here? Natural log of y equals 7.064699 plus 0.365835x. If I take base e, now that means that all of this is the exponent on base e. So I have y equals, and then I have base of e, and I have 7.064699. Now, what does plus mean in exponents? It would mean that I could rewrite the base again and say that this is 36585x. Okay, this number right here, think about that. That makes sense, because if you were doing x squared times x to the fifth, wouldn't that be x to the 2 plus 5? So I'm just reversing that process, taking it and splitting that plus apart. But anyway, this number right here is that 1169.93. This number right here, with its raised to the x, this number is 1.4417. So that's how, using some properties of exponents in algebra, I can actually come up with the exponential model. So when you have something exponential, you can always try using the exponential model on the calculator, that key, or write it in logarithmic form like we did originally. Okay, so I'm just going to put the equation back in. So I'm just going to run the stat, because I want the residuals to be in the calculator's memory. So if I run this again with my L1 list and my L3 list, because remember that's where I put the natural log, and this time I think I'll even store the equation in there in my, how do you do that? You hit vars, and then it says y variables function to put it in y1, and then it's going to store the equation in there. Calculate. Okay, so that's stored in, and now I want to graph it. So I'm going to go into my stat plot, which I actually already have on, and I want to do the scatter plot to check the L for liner. And so I want the scatter plot on. I need to make sure that I am graphing my x and my y, which was an L3, because that's where I put the natural log of y, that I'm graphing that. So zoom 9, and there you have it. So that satisfies my scatter plot of L1 and the L3, which is the natural log of L2. So that's looking very straight. I've satisfied the L. Then you would, of course, check your independence. Then nearly normal. How do we check that? We use the residuals, which we just found out we can actually check really easily. So let's go in and do that. Okay, so first of all, a histogram of my residuals. So I need to pull in the residuals list, which by hitting second stat, I can get to all the lists that are in the statistics thing, and there is a residual one there. So, and then I'm going to just hit zoom 9, and that looks, the histogram looks symmetrical. Now let's do a box plot just to make sure that it, no outliers, because that would be a problem. Okay, so I've got the box plot selected, zoom 9, no outliers. Now the normal probability plot, which actually is probably more powerful anyway. Normal probability plot for the residuals, just get all these residual things out of the way. And so zoom 9, and that looks very straight, because remember we want the normal prob plot to be straight. So I would say that we have, with maybe a little bleep in there, but like, you know, I would say that that fits the situation for the end condition. And liner, continuing with E and also with R, that's the randomness. So you check your randomness. This E, let's check that. Let's see. That would be checking equivariance. So we're going to want to have the X on the X-axis, but we want the residuals on the Y-axis. That's a residual plot. So if I go in and do a scatter plot of, now I've got to move my L1 back to there, and I need to bring the residuals in. So selecting the list, which is nice. And then if I hit zoom 9, I can see that plot. What's interesting about this is there definitely does appear to be a pattern. You know, there does appear to be some patterning to this. Which would really support the idea that I said I wouldn't want to use this model for any kind of extrapolation, because this model does seem to have some issues. However, if you trace along and look at the residuals, they're actually quite small. So those are very small residuals. So your prediction error being quite, you know, not that much off. So down here, maybe a little bit more. And over here, I mean, as we get into the later years, it seems to be going off a little bit. So because the S is small, well, what is the S? I guess probably the fastest way to find the S would be to just run a, let's just run a test on it. Let's go second, oops, sorry, stat tests, and just run down to where, how do we get those? Go down to these tests that we did in 12.1, the linear reg t test, the linear reg t interval, but I'll do the test, and I'm going to do this with the L3 list. And if I go down and I just go calculate, then I can get my standard error of the residuals really quickly. So my S is small. The S was equal to 0.544467, the units being natural log transistor. So that's basically my thoughts on there, is that I probably would use the model for especially those lower years, but I would not use this model for extrapolation.